guys, but I really like to fuzz. I like to find vulnerabilities and post them up and make a little money on the side with the bug bounties and get some CVs. So before we go on, props to ANYCON for 2 years. This is great. I spoke here last year. This is like a wonderful conference. I hope ANYCON keeps going. It's a really good group. It's in an area that doesn't have so many cons going on all the time, so it's also great for that community. This is me. I'm John Dunlap. I have stuff like this. This is this year's MacOS Privesk. I found a privilege escalation in the cup statement. It turns out that it lets you set. It lets you set. Are we still on the mic? Yeah. Okay. It lets you set environmental variables, which is bad. I also hack like this. I do a lot of reverse engineering kind of stuff. That's Binja, if you've never seen it. It's kind of like IDA Pro. I also hack like this. That's bacteria. I do genetic editing and like hide encrypted data in living organisms. So this is me. If you want to get in touch with me, at John Dunlap too. That's my GitHub. You can check out I have an automated tool for developing the encrypted organisms if you want to try that out at home. If you happen to have like a CRISPR setup or some other similar plasmid editing software, hardware, you can do it yourself. I talk a lot. Here's some of my previous talks, DNA encryption, machine learning, FPGAs, even hacker history. We did at Hope. I hope somebody saw that this year. 3D printer security, and last year at ANYCON we talked about jump-oriented programming exploits. Had a great time. I don't know if you noticed there, I spoke at DEF CON 3 times this year on one day. That is a lot. And this was happening. There was a sandstorm. I think I still taste the sand. So let's go on with it and talk about our actual topic here, this fuzzing cluster. This is for anyone who's sort of interested in building a bigger than natural, bigger than casual fuzzing setup, but you're not quite Microsoft. If someone here is from Microsoft or Facebook or some other large company, or Equation Group or something, if you're sitting in the audience, this is not going to be as good as what you do. This is going to be sort of a more brittle, more high-performance thing that's meant for people who have more time than money, but want to save some time, save some money. The sort of motivation for this was that last year I was doing a talk on 3D printing security, and I wanted to fuzz a specific type of program called a slicer. We'll talk about that in a sec, but I was not able to actually fuzz slicers with the available fuzzing tools. If you're not familiar with fuzzers at all, you're generating like sort of randomized test cases for a piece of software, hoping to crash it, hoping to uncover a crash condition that will lead to an exploit. Now, I really wanted to fuzz this slicing software, but it turns out the slicing software itself was not performant enough to do fuzz cases. You could generate even relatively small 3D printable files, like very minimal test cases, and it would cause the fuzzer to sit around waiting, computing for perhaps hours. And that didn't work. So what I wanted was a semi-automated high-performance system that I could use to compute, big things, to do a lot of fuzzing at once, and just handle all the workload of managing the jobs and splitting it up. So that's what I wanted here. If you've never seen slicing software, what it is sort of the compiler step of 3D printed software. Like basically, you take a 3D printed model and it analyzes it, it gives instructions for what the 3D printer is going to do. It turns the 3D model into G code that moves the stepper motors. It's very non-performant on just about every slicer that exists, and we want to get past that. So we're going to talk about porting some high-performance compute optimizations into traditional fuzzers and smart fuzzers. We'll talk about standard techniques for speeding stuff up in general, and then we're going to apply those to the fuzzers. We want more crashes, we want better crashes, we want more of an ability to triage those crashes at scale, or like medium scale for us. All right? But we're going to have to make some trade-offs as to how and if and why we're going to do that. Like I said, we can't just throw infinite compute at this. That means that we might have to customize the target software in certain ways and make some smart decisions about where we could maybe give some of our engineering effort to get more out of the fuzzer instead of just throwing node after node at it and cleaning up the mess that results. But I'm not the first person to think of this kind of thing. There's all kinds of scalable fuzzers. Like I said, Google has OSS Fuzz, and you can check that out on GitHub. Maybe in a future version of this talk, I'll run down exactly how that stacks up to what I'm doing, but it's pretty darn good. Facebook's has a distributed fuzzer. There's the Nightmare distributed fuzzer. There's various people trying to tack OpenMPI onto AFL. These are all pretty darn good. But we'll go over some of, like, say you want to do this yourself, or you want to make something really custom and sort of set up all the bits and pieces of it as you would for a scientific computing setup. We're going on the model of like taking something that would normally be for like doing Monte Carlo calculations and porting it over to doing fuzzing. So what are some of our high performance compute optimization techniques? And you keep in mind, we're talking about, like, I'm an optimization script kiddie. I am a programmer. I do a lot of low-level stuff, but I don't work for Sandy International Labs. I don't do this all day. So we're going to have, some elite techniques coming up. And I'm going to warn you, there's going to be a lot of talk about these two guys. It's not an ad. I'm not trying to, advocate for one or the other, but this is the sort of performance arms race that's going on in computers at the moment. Okay? So here's the techniques we're going to go over in general. Okay, Simpie Optimization, I'm sure that a lot of you have heard that, single instruction, multiple data. Threading, OpenMP, cache optimization, same system multiprocessing, we're talking about stuff like OpenMPI, GPU acceleration. We're not going to talk about FPGA acceleration, unfortunately, too much. And then maybe using an optimizing compiler. What we're not going to talk about is stuff like improving the big O, improving the algorithm, which can actually be a more profitable thing, but in a lot of cases with fuzzing, we don't have that choice. It's not necessarily a thing we can do, and we'll talk about why that's not necessarily the most profitable idea all the time for our goals, right? So moving on, let's talk about Simpie Optimizations. If you're not familiar, we're talking about same instruction, multiple data. There's basically assembly language instructions that let us operate on what used to be scalars like 5 times 5 and work on vectors, 5 5s times 5 or something like that. And Intel supports this on the large computers up to 512-bit. It looks kind of like this. We can have 8 floats or 4 doubles, and that has the potential to speed things up a lot. And the way you do this, if you're altering some software to do it, is to add Simpie intrinsics. You could write assembly language by hand, but as we'll talk about in a second, as we examine each of the fuzzers and fuzz cases and the use case scenarios, we don't want to alter too much of the program. If we're talking about the target program, and altering the fuzzer might not be worth it. So we'll talk about that more later. And of course, as soon as you bring up doing by-hand optimization, someone in the audience is probably going, you can't do that, the compiler's better, and it's not always true. One of the things you got to keep in mind is that the compiler is incapable of understanding every use case. One of the things that compilers are classically bad at is understanding data dependence issues. And even on a very high-end, talking Intel's optimizing compiler, you have to sometimes nudge it a little and go, actually, those are independent data. You can't optimize that. So there's pragmas for that. And if you don't know what I mean by data dependence, we'll show in just a second. But you don't want any case where you parallelize data as depending on previous cases, like this situation. So we have Fibonacci sequence, and each iteration of it depends on the previous iteration. That means we can't unroll that loop into 8 Simpie operations all at once, because each iteration of it depends on the previous one. So we can't do that. But if we're just doing standard matrix multiplication, we can. So that's good. And that's going to impact our performance. Most people are aware of threading, and most people are afraid of threading. And as we'll examine later, threading might not be the answer for our fuzzer problems, because limitations of the resources in the computer. But sometimes it can give you big gains, like in normal scientific computing situation where you're working on a very small algorithm that's being widely parallelized. you can get like 10, 20 times speedups. And this is how you do it in OpenMP. You can just add this pragma that says parallelize this. And this blows the mind of people who have tried to do like GNU threads, like P threads, and have gone through the pain of that. With OpenMP, you can just be like, make it parallel, and that's the critical section. Actually, it just kind of works really well, and it's not as scary as some people would think about it. Then you got cache optimization, which, again, we'll talk about. It sometimes fits what we want to do. This is going to be system dependent a lot of the time. It can be a really, really huge performance optimization, but it's not something that we can think about doing automatically. So we can't like programmatically mutate the target software to work inside of our L1 or L2 cache. And that sucks. Most people are afraid to like get their hands dirty doing this, but it is possible, but the trade-off for engineer time versus profit is like, not so great, especially in our use case. We'll talk about that later. There are also some special caching architectures you can get into. Again, I'm not advertising here, but Intel Phi has, Xeon Phis have this thing called the MCD RAM, which is like a high-speed shared memory architecture that you can actually use their optimizing compiler to say, put this in MCD RAM, and if your entire program or entire subroutine fits in the MCD RAM, it runs lightning fast. It's a huge difference, and it is slightly automatable. So that could work if you have the optimizing compiler and you have the MCD RAM, and maybe you don't. Maybe your VPS provider doesn't give that to you. Maybe you can't get that off Amazon or DigitalOcean or whatever. And then we're going to talk about MPI, or message passing interface, and just the idea of spreading this over multiple cores and multiple hosts. MPI gives us the tools to do this so that we can send messages between the various sub-processes and get stuff done. And this is probably the most applicable thing for fuzzers, but they already sort of do it to various degrees. Here's what OpenMPI looks like. Here's more. We'll get going through this quickly. Then we could just like throw all that stuff out the window and redo the entire algorithm on a GPU. And this is something that a lot of people are trying to do. There's a lot of ongoing research on it, but there is no like GPU dedicated fuzzer, because translating your algorithm into something that's going to run the GPU might change the semantics of things, and you might not get the same crashes. It's hard to find where to put the work on the GPU for this particular use case. But it does make stuff like really fast. So let's talk about our HPC stack that we're going to build. And to people who are familiar with HPC, if you've done this in like a college setting, it's all going to be about the same, and it's all kind of open sourcey and easy to put together. So the first thing we want is a job queue. Then we want some way to pre-process our fuzz jobs. Then we want to run our fuzzers. Then we're going to do a crash triage. And then we're going to sift through our output for the answers that we want to get. Now, for the job queue, we want some way that we're going to be aware of how many system resources we have, how many nodes we have to use, how much room the nodes have. Basically, what I went with was open grid sended type thing called Torque, which is available on Ubuntu. It's easy, and it conforms to, if you've used like QSub and that kind of thing in college, it works just like that. And allows you to submit a job to the queue, and it'll take care of the rest for you. And then, if you're running something like AFL, like a smart fuzzer, you might need to carefully design your fuzzer job pre-processing so that you're not losing performance there, where you might have to instrument binaries for this to work. So you might have to like recompile these each time you're about to set up. So that's a step to consider, but not one we can really optimize without changing the semantics of the fuzzing software. So we're not going to talk about that too much. But we are going to talk about some fuzzers and how we would optimize them and where the sort of performance trade-offs work out for the purposes of the experiments we're about to do. And then we're going to talk a little about crash hiding tools like this. And then we're going to string it all together and try to get a profitable result. So once again, we want the largest number of crashes, and we want the most high-quality crashes. So let's take a step back and sort of consider the options for applying the optimizations we just talked about to our HPC fuzzing cluster setup. We have a good idea of like what we want the architecture of the thing to be, but now we have to know like how can we make this faster, because on its own it might not be worth our time. Okay? First of all, we'll consider like optimizing the fuzzer. And one thing to keep in mind is that although we're talking about fuzzers in this talk, the fuzzer itself might be doing only a fraction of the work itself, right? The fuzzer might run way more performantly than we ever need it to. It's not what's holding us back. It could be context changes like forks that are holding us back, where we're invoking that child program, the target program, and it could be the target program itself that's holding us back. So we might think of like ways to automatically optimize the target program in such a way that we're not changing its semantics. In a typical AFL fuzzing situation, a lot of times the limiting factor is the call to fork, and we're waiting for the context change from the operating system most of the time. So finding ways to reduce that could be good. But we'll consider how we could lower the cost of our fuzzing, even though we know that's probably not the main source of waiting around, right? And we could add Simpie, right? We could recompile AFL or whatever fuzzing solution you want. You use the fuzzers available for Clang, for instance, and make sure to put the full complement of Simpie. And that might be done automatically on your system, but a lot of times the default compilation setup is a little conservative. You might be set to compile with AVX 256 instead of 512. So manually specifying that might get you a little more performance out of the compiler, but it's generally kind of not, only barely worth it, right? But you might do better by manually setting it. In my experiments, I got maybe a 2% speed up, probably negligible, out of sort of recompiling AFL with the maximal AVX setup, so with 512-bit. And one of the reasons that is that it doesn't spend a lot of time doing things that are amenable to Simpie operations. What about OpenMP? Well, again, because of the way fuzzers work, we're sort of expending all of the threads on the system, so we don't have a whole lot of threads to give. So that might not help us up as much as we would hope it would. So we might toss that. And for MPI, yeah, that sounds like a great idea. If we can just throw this on a bunch of clusters, a bunch of nodes, that might make things faster, but the return on investment isn't as good because we have to pay for all those nodes. And again, nature of the fuzzer, because we're spending most of our time context transitioning to the child program, optimizing the cache is probably not going to be a thing. So what about the target software? So when I say the target software, I'm talking about we're going to fuzz libpng or something like that. What about optimizing that? Is there ways that we can optimize the target software without hurting the semantics of it and missing out on crashes? It's probably possible, and it's probably where most of our workload is sitting, at least in the way I fuzz things. Now, with Simpie, this is very dependent on the exact workload of the program, on what it's doing. If the program is doing stuff that is kind of vector mathish, if it's doing a lot of matrix multiplication, like, I don't know, libpng might, then yeah, we can get a pretty good speed up. Dependent, right? And we could get an even better speed up if we did this manually and use, again, Intel optimizing compiler gives you a way to manually specify places where you want this to happen. The downshot is that's a lot of manual work up front, and if your personal cost of labor is more than you're getting in terms of speed up, it might not be worth your time. Just making sure you have the optimal Simpie set up automatically from your compiler, using the optimizing compiler when you can't, you might get your best return on investment. With the target software, OpenMP, basically trying to add more threads, again, it's really hard to get any gain out of this because the fuzzer is using up all the threads by running jobs in parallel. So we might not be able to get an automatic speed up this way, but we can kind of think about maybe there are ways that we can be smart and try and use the threading in a way that's more advantageous. This is kind of a thought experiment because I'm still in the process of implementing some instrumentation, some changes to the binaries added in the fuzzing stage that would automate this. But what if we only threaded the parts of the program that are invariant, right? What if we only split that up and then serialize the bits that are changing, the interesting bits, or the opposite? Would those be worth a try? That's kind of an open question that I'm trying to answer over the next 6 months. What about multi-programming, message passing interface? Yeah, I mean, lots of people are already doing this. This is the easiest thing. But again, we're doing this synchronously with the fuzzer at this point. An interesting thought experiment is there a way to get more out of your OpenMPI by doing it asynchronously from the fuzzer, by setting up different sort of relationships between the child processor and the fuzzer? Can we do stuff in batch separate from the fuzzer while the fuzzer's waiting around? That is a more interesting question. With the triage software, we have sort of the same problem, but running double. Because when we're triaging crashes, although we have much fewer crashes than test cases, we're going to usually be invoking a debugger, and that debugger is going to be invoking the target software and running it till it crashes. And you can see we're like really suffering not one, but two, but probably 3 context changes, and that's going to slow things down a lot. But going over the existing optimizations, there really isn't much for it, right? Other than trying to find a way to redo the entire structure, the entire architecture of this setup so that we don't have to do those crashes or do those invocations of the debugger. So, what we learned in this section of the talk is a great majority of the work is done in the child process, and optimizations to the fuzzer itself don't make as much difference to the overall performance as optimizations to the child processes, generally. I'm sure there are special cases where you're running especially small programs, and the fuzzer is able to outweigh the child programs. But most of the time, we're either context switching and waiting because we don't have enough threads, or we're waiting on the child program to finish and crash. So what I did to do some testing on this was to construct sort of a fuzzer race, and sort of design an informal experiment to see like how these optimizations sped up, strictly speaking, the automated ones, and whether we could design like little automated fuzzing HP system that would be profitable. Okay? So here's our experimental design, informally. We're going to set up our little imaginative fuzzing cluster setups and try and learn from the performance like this. First we have a VPS setup on DigitalOcean. Let's see, in fact this slide is wrong. We actually did 4 nodes and a control, so 5 total images running torque for control queuing. And with these setups, and here's my DigitalOcean cluster, and here's some of the performance of it running with like I'm computing digits of pi or something, a few nanoseconds. And then we're going to take our target software, in this case Object and libmagic, and sort of count the number of crashes we can make. We're going to time it to 10 minutes and run it against the control and see if we can get a bit of a speed up, and see if ultimately all of this is worth our money. And here are the sort of raw, very rounded results, and we see a little bit of improvement from SIMD could be worth it, especially on Object. For some reason, gets a lot out of it. When we do the multi-programming, it's a huge increase, but it's a whole huge increase in terms of cost, and OMP gets us almost nothing. I promise I'll give you a better graph in the future. Watch my Twitter. I really hate Mathematica, and like there are moments when I'm doing these talks where I'm like, oh my god, how did it go? So you might have some questions. I'm going to cut a few off at the pass here and just kind of answer what might already be in your brain. Like what did we learn from this? Again, as we already knew, distributing across multiple nodes works very well, but doing the automated SIMD gives us a nice little boost that might make things more worth your while. how much did this cost me? 4 nodes is like $300 a month. You know, and these are the high-speed DigitalOcean nodes. They're not the basic ones. They each have like 4 CPUs that are supposed to be dedicated-ish, and it's pretty fast. If you're asking yourself what the break-even, if you want to try this, you just got to ask yourself, can you make $300 a month disclosing vulnerabilities? And I think if you're into exploit development, you could probably do that, right? And really, at the speed that this is generating crashes, you could do a lot better than that if that's all you did full time. You might be asking, would this be cheaper with an at-home setup instead of a VPS? Because everyone's worried about, you know, the VPS is like a multi-home kind of thing. Maybe the performance is not the best. No, because you have to pay for power, you have to pay for cooling, you're going to destroy your stuff. You know, I can run DigitalOcean's VPSs into the ground and not have to worry about my CPUs melting. So keep that in mind. And you know, the parts that we didn't talk about in this talk is like a slick system to integrate this, to visualize it, to deploy updates. That's not here. My continuing research in this direction is I'm working on several methods to sort of automatically GPUize fuzzing setups where we take repetitive work in the test case and move it over to the GPU so we can get the status of the registers to where we need it to be ahead of schedule so we spend less time in the test case. Investigating ways to speed up fuzzing with machine learning. I'm about to link you a paper where they use neural networks to get us, again, where we want to be faster. And also, you know, if you notice, like one of the key breaking points here is all the calls to fork, all the exec calls in this, and finding a way to restructure everything so it sits in memory all at once and we're not constantly calling for it is a good thing. I don't have much to say about GPU accelerated fuzzing. It's still kind of nascent. Here's a paper on the neural net-based fuzzing. If you're interested, you should check this guy out. He's at Microsoft. He does very cool work. And that's about it for the main part of the talk, but I'd be glad to take questions if you have them. Yes?
If you are dealing with a program that has, say, like a lot of bootstrapping or libraries that need to be pulled in to the part where you want to start fuzzing, can you leverage copy on write to sort of like get that initialization out of the way and then spawn child processes from that breakpoint?
Well, yeah, you could, but the problem is doing that in an automated way, right? Where you're not going to change the semantics of the child program. And you know, one big piece of research that has been going on, it's not new, but it's definitely not in the limelight of sort of automated software testing research, is the idea of slice testing. Finding a way to automatically slice up the program into component bits and testing them separately, because obviously that will be a great deal more performant, and we don't have to deal with the problem of getting up to the place, right? But then you have to deal with the question of, is everything in the same state semantically that it would have been if we had worked our way up naturally? So, you know, it's different situations where, like, are you able to totally fuzz library calls independent of each other? Sometimes that works, sometimes it doesn't. Sure?
What would typically be a target for this kind of fuzzing?
So the easiest thing to do with automatic coverage guided fuzzing is native programs that take a simple file, like libpng is great. You know, you can do conversions of image files, right? But you can do it with protocols and stuff. It just takes a lot more bootstrapping to set up the communications ahead of time. Like a common paradigm when people do like OpenSSL type fuzzing is they have to like reprogram the server and the client into one program so that you can just send it test cases and not have to deal with the like TCP communications. Sounds like a pain, doesn't it?
Yeah, been there.
Okay. Any other questions? Okay. So this is my contact. If you want to get in touch with me, you can also, they're not up yet, but like tonight the slides are going to go up here. And the script I use to launch these will come up soon. I want to give a non-buggy one where I'm not disclosing a password or something. I'm a security engineer. I don't want to do something silly. And I'm doing like part 2 of this talk at B-Sides DC. So thanks everybody.